have a tutorial and the title is Introduction to Assembly Language. Now I give this tutorial to you because originally we should have 3 laboratories. 2 of them involve the lab of assembly language. The processor we are going to work with is 8051. And therefore, we better give you more information about this processor. Now, firstly, for the assembly language, just we have told you in the lecture that it belongs to the middle level language, or sometimes we say that it is low level language because it is just above the machine code. And it is different to the C or Java language because they are the high level language. And now the reason behind that we write the assembly program because it can provide the program with small size and fast speed. Okay. And here we show you the general computer architecture for the 8051, and you can see that in the middle we have the CPU. Okay. And for 8051, it is a 8-bit CPU. That means the data width of the processor can be handled is 8-bit only. Okay. Now, therefore, the you may think that 8051 it is not very powerful. And in the market, you can purchase a 8051 at around $20 to $30. Okay. Now, other than the CPU, it requires some input device to give the external stimulus to the CPU, and it can respond to the stimulus by giving the response out to the environment through the output device. And the CPU can store the data into the memory. Okay. Now, and we will explain to you mainly what is inside the CPU. Now, we show you the CPU architecture in figure 2. Now, you can see that in 8051, the internal structure is more or less the same to the other processor. We have the program counter. It stores the current address that the program is being executed. Similarly, we have the instruction register, which store the current instruction. Okay, and we have the instruction decoder and control unit, and basically the opcode stored in the instruction register should be decoded. Okay, the decoder means that one of the pin, the hardware control, will be enabled depends on the instruction. Therefore, we have the decoder and control unit in order to control the ALU or the other operation to perform. The ALU, we have just told you that it mainly carry out the addition, subtraction, or logical operations for the data. And it consists of the register array. You store the registers. And now for the 8051, we told you that during its read-write cycle, we can follow the procedures in order to read the data from the memory or write the data from to the memory. Okay. Now in the read cycle, now we have 5 steps. Firstly, the CPU places the address on the address bus, and then it sends a control signal to the memory to indicate the address is valid. And then the memory chip first fetch the data from the location specified by the address and paste the data onto the data bus. And then the memory chip will send a signal to let the CPU know the data is valid on the data bus. And finally, the CPU takes the data. Now this is the read cycle. Now on the other hand, we can have the write cycle so that the CPU writes the data to the memory. Again, we have 5 steps. First step, the CPU plays the address, and then it sends the signal to control the memory that the address is valid. After that, the CPU will place the data on the data bus. And after that, it sends a control signal to the memory to tell the memory that the data is valid. And finally, the memory chip takes the data and pastes it according to the location specified by the address. Okay. Now in here, we can work with a read-write cycle simulation so that you can have more understanding on the read-write cycle. Website into the browser, you can reach to this web page, and you can see that we showed you a simulation about the read-write cycle of SEHS3317, and we have read cycle and write cycle here. So we try the read cycle first. Now in the read cycle, you can see that on the left hand side you have the CPU. On your right hand side we have the RAM. Okay, and for in the RAM, you can see that the address is labeled. Okay, and in between we have the bus connecting the CPU and the RAM, and we have the blue address bus, green data bus, and red control bus. So if we send an address from the CPU, that means the CPU requests a data from the address 000, and you can change the address by pressing the combo box. For example, now we try to obtain the data from the RAM with the address 002. So you can press the CPU request data button here. Now 002 will be put onto the data bus. Okay, and now you can consider that the address is sending to the RAM, and you needed to wait until the address is valid. And now the RAM chip is know that 002 is sent by the CPU, and now the CPU can send the control signal to the memory to let it know the address is valid. And then the RAM will send the corresponding data to the data bus, that is CC. Okay, 002 is in this location, so CC is putting at the bus, and now the memory chip will send the control signal to the CPU that the data is on the bus. And at the end, CC will be written by the CPU. Okay. Now, so you can try the write cycle by yourself. You can press the start again, and this time you press the write cycle to see how you can write the data to the from the CPU to the memory. Okay. Now we go to the execution cycle. You can see that now for the execution cycle, That means the CPU execute an instruction. It first access the program which is specified by the program counter. The program counter means it stores the current address to indicate which instruction is now execute. And then, according to the instruction, the program counter, the CPU fetch the instruction and put it into the instruction register. And the instruction in the instruction register will send to the decoder together with the control signal to decode the instruction and ask the corresponding hardware to perform. For example, you may ask the ALU to perform the addition. And after the instruction has been completed, the program counter will be automatically increased. Okay, so we have the execution cycle for the CPU. Now here we have the execution cycle simulation, and you can try using this website. You can reach to this web page, and you can see that in the execution cycle, it performs 6 steps, including the content of the program counters are placed on the bus, and then send the control signal to the worm to let it know the address is valid. The worm select the location and then put the data onto the data bus, and then it will send the signal to CPU to indicate the data is valid. And then the data on the data bus will put into the instruction register to decode and execute, and the cycle will be repeated. So let us press the Start Simulation button, and you can see that at the beginning the program counter is 0, 0, 0, 0. Okay, so when we press Next, you can see that the address bus has been updated to 40. And then it will send the control signal to the worm to let it know that address bus is valid. The address is valid. And then the worm will return the data storing at the address 0000, and then put it onto the data bus and send the signal to the CPU to show the data is valid. And now you can see that the data or the instruction has been stored into the instruction register, and it will perform the execution. Okay, and then you can see that the program counter will be automatically increased by 1 to indicate the next instruction will be fetched. So the cycle will be repeated. You can see now the address 0001 has been put into the onto the address bus. Okay, now here you can further investigate how the CPU execute the instruction using this cycle. Okay, now we move to the part about the 8051 pin assignment, and you can see that for the CPU it contains 41 pins. Okay, and most of them belongs to the ports. It has 4 ports. Okay, 4 ports: port 0, port 1, port 2, port 3. Now they are the I/O ports for the 8051 to connect to the other device, and we have the other pins so that we can make the connection to make the 8051 to run properly. Now please pay attention that for the port 0, it is used as the address and data bus connection. Therefore, A stands for address, D stands for data, and it is a 8-bit bus or 8-bit port. For P2, it shows to you that it can connect to the address, the higher address from A8 to A15. Now that means 8051 has the ability to access 16-bit address. Okay, we combine two ports to form a 16-bit address. Now for port 0, it is pin 32 to 39. It used for address and data. It shares the address bus and data bus. For port 1, it is a general I/O port. Okay, when you are going to connect to other device, you may use the port 1. For port 2, it can use to connect to the external memory because it supports the higher byte of the external address. For port 3, it is another general I/O port, okay, but it can carry alternating function, and because you can see we have different name for each pins of port 3, and we indicate the function in this table. RxD, it is a serial port. It mainly used for receive data. For TXD, it transmits data for the serial port. And 8051 has two external interrupt 0 and interrupt 1, and it is connecting to pin 2 and pin 3. And later we will describe how the interrupt function in the computer system. Pin 4 and pin 5, they are the timer. Okay, that means it can send an internal clock signal to the other device, which is connecting to H051. And pin 6 and pin 7, they are using to control the external data. With pin 6 is specified the white stroke. That means after we put enable this pin, it asks the memory that the CPU is ready. And similarly, for the red stroke, it tells the memory that the CPU is ready. The reset pin means that when you press the button, the CPU will perform the hardware reset, and it will load the program stored into the booting ROM, or what we call the startup program. For the EA bar, it means that it is a effective address. Okay, it tells the memory that the address has been valid into the address bus. Now the label we given to you that EA, actually we have a bar on top of EA. It means that the logic is reversed. When it is used, it output a 0. Okay, it employs the negative logic. Okay, now therefore we describe that when it ties on 5 volt, the CPU will execute the internal ROM. However, when it is tied to low, that means 0, the effective address can be enabled, and it can execute the instruction from the external memory. Okay, and we have different versions for 8051. For example, 8052, we have the ROM. We have a larger ROM, 8K. For 8031 and 8032, we do not have internal ROM. Okay. The ALE means the address latch enabled. When using, it means that we are using the address is valid on the address bus. Okay. And for the PSEN bar, okay, actually it is the pin 29, and it it is used to fetch the instruction from the external code memory. Okay. Now here we show you the memory organization of 8051. Now it has internal ROM. ROM, it is a memory that once you burn the code onto the ROM, it cannot change anymore. Okay, that means you can write the program by one time during the manufacturing, the ROM manufacturing. In 8051, it has 4K, or the exact location is 4096 bytes of ROM to be used. It can store the system program. Therefore, when you press the reset button, the CPU will automatically fetch the program from the ROM. And the internal ROM address is 16-bit because 2 to the power 16 equal to 40996. And the ROM address is specified from 30 to 3F in hexadecimal number. Now it has also the internal RAM. The internal RAM means that it can read write, but the size is much smaller. It has 256 internal RAM, and sometimes we call them the register. Okay. Therefore, the address, now we have 8-bit address to access the RAM or the register, and the memory, it is range from 00 to FF in hexadecimal number. Now, here we show you the diagram about the arrangement of the internal RAM. The first 1 to 8 location with the address from 00 to 7F, they are the memory can be used by the programmer for storing their data. However, the higher order or higher address location from 80 to FF, they are so-called the special function registers. Okay, and we will show you the function of this register later. Now you can see that the diagram shows you on the left-hand side we have the lower byte address. Okay, it shows you the general purpose register. To the right-hand side we have the FR. Okay, they carry special function. Now we will introduce them to you one by one. Now for the register bands, you can see that we have 4 bands here. Okay, and by default we are using the 8 register in band 0. Okay, and you can switch to another band by using the status register. Okay, the band 0 has the RAM address equal to 00 to 07, and band 1 we have 08 to 0F, band 2 we have 10 to 17, and band 3 we have 18 to 1F. Okay, and if you have changed the band, that means when you write the data, for example, if you change to band 2, if you write the data to R0, that means you are writing a data to the address 10 in the RAM. Now higher than the 4 band, you have the bit address location. That means starting from 20, all of the register can be, each of the bits can be manipulated each one by one up to the address 2F. Okay, and they are actually to manipulate individual bits. You may using them to turn on a light. For example, you set this bit equal to 1, it means you are going to turn on something, turn on a light, or put a 0, that means you can turn off. Okay, so it makes the CPU become very powerful in control the other hardware, especially when they require the turn on or turn off signal. Okay, and the number of bitwise address location equal to 2 to the power 10. That means we have 1024 address that you can set individually. The address of the RAM range from 20 to 2F, okay, and they are where some of them are located in the FSR, the special function register. Each of the 128 bits from 20 to 2F have a unique number to that means the address, and the 8051 instruction allow the programmer to set or reset any single bit in the RAM. Now higher than that, from 30 to 7F, they are the register band. They are similar, and they can read write to full bytes only. Okay. Therefore, now if you are going to using the bitwise operation, you may use the address 20 to 2F. Okay, and later we will show you how we can use this RAM to perform different functions. Now starting from the address H0 to FF, now we contain the special register. And you can see that not all the location is used by the 8051. Some of the locations are banned because the other family may have different register occupy that address. And not all the SFR are bit addressable. Some of them, when you access, they can only read the address only. With the byte address only. And now we can deal with the each SFR during our program. And for example, you can notice that the accumulator, that means it is mainly used for the ARU, locating at the address EO, and the port register is locating at HO, 90, AO, and BO. For P0, P1, P2, and P3 respectively. Now that means instead of writing or using the name of P0, you can directly write the data to H0. The effective operation means that you write a data to port 0. Now for the missing register, you can, as we told you that actually, two of the important registers has not sold you the address. They are the program counter and also the instruction register. Okay, because they are the most important register in the CPU. Therefore, we don't hope that they can be accidentally written by your program. Therefore, we protect it and do not release its address. Now, here we have a register so-called the program status word, and it is located at DO, and it is bit addressable. And for individual bit, it shows you the meanings here. For pin 7, it shows you the carry flag. Pin 6, it is the auxiliary carry flag. Pin 5 is a flag 0. It indicates it is a general purpose flag. You can the programmer can set this flag to indicate the corresponding status. The next two pins representing the register band selection. Okay, and pin number 2 we have the overflow flag. Pin number 1 we have the reserve flag, and finally pin 0 we have the even poverty flag. We will introduce each of the flag to you one by one. Now for the carry flag, it means when you perform an addition, whenever the result require a carry, then you needed to set this flag. Not set by the programmer, but the CPU will set this flag automatically. Now, for example, if you are going to add 3 to this data, FDH, the result is something like 100 with a carry appear. Okay, so the accumulator will store a 0 and the carry flag will set. That means it is a 1. Okay. Similarly, when you perform the subtraction, and it will indicate a borrow. Okay, for example, if you contain a number 3dh which is going to minus a data 4bh, because 4bh is larger than 3dh, therefore after you make the subtraction, the carry set will also be set because it indicates it has a borrow. Okay, and also we can manipulate the carry flag by using the bitwise operation. For example, you can perform the AND operation to the bit 3dh with the carry flag by using this instruction, and the result will be put into the carry flag. Now, for pin or bit 3 and 4, they are going to use to select the register band. Remember, we have 4 register band in the SEHS3317. Therefore, by issue a command to control pin 3 and pin 4, you can select different register band. Here we give you the table. If you put a 0, that means you are selecting the register band 0. 01, you select register band 1. 10, you select register band 2. And 11, you select register bit band 3. Therefore, if you are going to, for example, you are going to activate the register band 3, you may issue the instruction set bit RS1 and set bit RS2, and it makes the register band selection bin will become 11 in the status register. Okay, and now if we move the content of R4 to accumulator, then the content will move to the data from the location 1ch, because now you are having select the register band 3. So the data in the location 1ch will move to A. Now, flag 0, it is a general purpose flag. It can be used by the programmer. Whenever you needed to have a conditional jump, you may using this flag. And lastly, you have the priority bit, because it shows to you that the number of 1 in your register. And the priority bit is used that it always make the register together with the priority bit. They contain even number of 1. Okay. Now, therefore, if you have the accumulator plus priority bit is even, then the priority bit should be a 0. If the accumulator, the number of bits or the number of 1s in the accumulator is odd, then the priority is set to 1 in order to make the overall number to become a even number. Okay. So now we have the example. If the accumulator holds 0, 5, in binary we have 2 1 in the binary number. So we have even number of 1s, and the priority bit is 0. On the other hand, if the accumulator store a data F2 and you have odd number of 1, and now you can the CPU will set the priority to become a 1 in order to make all the 1 to become even. The number of 1 become even. And normally the parity bit can be used to detect the error in your transmission, in the data transmission. Now the register B, it is using with the accumulator for multiplication and division. For example, if you you write the instruction multiply AB, that means the data stored in A and B will be multiplied. The lower byte result will store in A, while the higher byte result is stored in B. For example, if now A contains F5, B contains 02, after you perform the multiplication, the result will be O1 EA, and O1 will store at B, EA will store at A. For the division instruction, it also carrying out by using register A and register B, and the result will be put in register A, and the remainder is put in the register B. So if the accumulator contains 07, the register contains 02, after you write the instruction divide AB, A will store 3, while B will store 1. Okay, and the register B is bit addressable, so that you can manipulate individual bits for register B. Now we have the stack pointer. Actually, it is a pointer to indicate the address of the stack memory. Okay, it is locating in the address H1, and the stack pointer is storing the temporary data, especially it is storing the address. Okay, whenever you have a subroutine call, you need to save the next instruction address into the stack memory, so that after the subroutine is completed, the program can continue the execution of the original program. And it is a last in first out buffer. So putting the data onto the stack, it means we push the data onto the stack. And on the other hand, when you take data off, that means it poke the data from the stack. Okay, the stack pointer, it contain or point to the address that is the top of the stack memory or the highest address of the stack memory. On power up and reset, it is automatically point to 07. That means the data will be stored into the register band 1 automatically. Okay, now the operation of the stack is that when you push, SP is increased by 1 first, and then the data will be stored, and then if you are issue the port command, the data will be taken off, and the value of the stack pointer will decrease by 1. Okay, so if the stack pointer point to 07, that means when you push a data, it will automatically save into the address OH, which is belongs to R0 of register band 1. Okay, if you wish to use the other location, you can change the stack pointer value. For example, you can change the stack pointer value to 3H, so that you can using the general purpose RAM of the CPU. Okay, so if you change the stack pointer, you can simply using the move command, and the stack pointer should be the address that you are going to use -1, so that you have 13 -1 and the result is 2F. Okay, and now we have some questions, and let us describe the answer of the question to you. Now the first question we are asked that when CPU begins execute a program, which register is used to store the address of next instruction? And the answer is very easy. It should be the program counter. And the number of registers stored in the SEHS3317 CPU is that now you can count the number of RAM because we consider they are the register. On the diagram or figure here, okay, you can see that on the left hand side we have 69 bytes because in the middle this 16 bit 16 times 8 are just corresponding to 16 bytes only. To the right hand side you have 21 special function register. Therefore altogether we have 117 register that we can use. Okay, we have 117. Now question number 3. Now if the value of the FAT register PSW is 78, what is the status of each FAT? 78, it refer 0111 and then 1000 in binary number. So you can refer to the diagram here. You put 0111 and then 1000. Therefore, you can see that only the auxiliary carry FAT 0, register band select 1 and register band select 0 are 1 and the other is 0. Now finally, we are going to execute the following instruction to see the current value of 07. Okay. Now, when you push R0, SP equal to 8, push R1, it is equal to 9, push R2, it is equal to 10, and then pop R0, the SP value will decrease, therefore it is a 9. Okay. Now I think we will use a few tutorial time to show you some other example, especially for the assembly programming for SEHS3317. And you may refer to this website because we found a very powerful simulator for SEHS3317. And you can practice your assembly language using the simulator. I will explain to you how we use the simulator later. Okay? Thank you.